Today we're going to continue looking at subatomic structure and particularly looking at the electron cloud in an atom. We're going to be looking at a way that chemists choose to figure out the arrangement of electrons in the electron cloud. It's called orbital notation. So yesterday, in the previous lesson, we started talking about atomic structure. Yesterday we made models of what the p orbitals actually look like. I mean, if you can see them. These are so small that nobody can see them. There's no way of taking a picture of them. At best, we have ways of taking pictures of certain atoms using a device called an electron microscope. There are different types of electron microscopes. But you have to be able to get the atom to sit still. The problem is that electrons are moving around constantly, and so there's just no way. There's no way that I can imagine we're ever actually going to get any kind of a photo, picture, map, or anything like that of electrons or electron clouds or the shape of those things. So we have to go by the information that we have from circumstantial evidence is available to us. The kind of address we're going to have here then isn't going to show you the actual shape of the electrons. But just like your address at home, these addresses can tell us something about where those electrons are located. Like if I see your address, I can tell what city you live in. If I know enough about the city, I can tell, what part of town you live in by the street name. Okay? So there's a lot you can tell from an address, and that's also true with what we're going to be learning today. So yesterday, just to remind you, we said if there was a nucleus here in the center of the atom, and then you've got the electron cloud around it, okay, and that when you were in ninth grade, when you were taking physical science, you were learning about the shape of main energy levels, okay, not the kind of energy levels we're looking at now. We're looking at things that are kind of go below those energy levels now into what are called sublevels and orbitals. So when you were in ninth grade, you only thought of these as having a nucleus here and having primary energy levels, and you could get electrons around the nucleus in those primary energy levels. And the first level would have up to 2 electrons, and the second level would have up to 8 electrons. And so forth, and you have more and more primary energy levels. And so now that you're in high school chemistry, we're beginning to look at what's happening inside these primary energy levels, how electrons arrange themselves within those primary energy levels, okay? And so that's where we get to this sublevels and orbitals, okay? And so we said that yesterday when we did our modeling with balloons, that if we were, say, in the second primary energy level, then we might have electrons that arrange themselves in these. Well, first of all, you've got an s orbital surrounding the primary level. So this is the s orbital, and there's a lower s orbital down here. This is the first primary level here, represented in the way you did it in ninth grade in physical science. And now we're in this second primary level, and that's this one right here. And within that primary level, then you've got these orbitals. Okay? So this double balloon shape that we made yesterday represents the orbital where electrons can separate themselves. So you have up to 2 electrons in this s orbital, up to 2 electrons in this p orbital, and so forth. Now, you notice that the lower energy level here, the first primary level, kind of cuts off the middle of that balloon. Remember that? Okay? Well, remember when we did a dotted line on your balloons yesterday? That's because the p orbital here actually doesn't include that area where the sphere is located, where the lower primary level is. Okay? So the p orbital is actually just the top half of these 2 balloons. And one of the strange things about electrons is they might be in this antinode over here. They might be in this antinode over here, and they might go back and forth between them, but they're not going to exist in here. So in a sense, from what we understand about the way electrons behave, is they sort of disappear from the universe and then reappear in the universe somewhere else. Okay? Spooky behavior, okay, for electrons. All right? And we can get up to 2 electrons in one orbital because of, what is it called? How can you get two electrons close to each other? Opposite spins, and that's what we call it in chemistry. If you were in another area of science, you might call it quantum entanglement. Okay? Those two electrons in the same orbital continue to talk to each other even after one leaves. Okay, I could have one electron here and one electron that was in this opposite spin quantum entanglement arrangement, and move that second electron into China somewhere, and they still would know which one's spinning which way, which is kind of weird, kind of strange, because you don't know what people in China are doing right now, right? Okay, but they know what their electron pair is doing. Okay, all right, and so we can have up to 3 p orbitals in a primary energy level. Okay, so there's the second p orbital. Remember, there's only the top half of it, and then you got a third p orbital that's kind of going out toward you and back away from you. I'm looking for another color marker, and I don't seem to have enough colors, but we'll use this orange one here. And so this orbital is like coming toward you, and it's back behind everything back here. Okay? And that becomes kind of strange to be able to draw that and see what's going on, understand what's going on, and that's when we did the three-dimensional models with actual balloons yesterday. So you can kind of see that. So when we're talking about this stuff, you have to be able to think in 3 dimensions. If you want to do well, you got to be able to see in 2 dimensions here on the paper or on the screen, and also think in 3 dimensions. Okay? And as we start talking about these addresses, then you got to be able to think in terms of, well, those electrons are there, but actually in 3 dimensions they're here. You got to kind of see that in your head. So I call that running the movie in your head. Okay? You got to have a little movie going in your head all the time to be able to think in 3 dimensions to do well. Now you can sit there and say, well, I don't need to know that. I just need to do what's on the paper, take my notes, and you can look back at your test grades and see how well you're doing. Okay? But if you're working at this, you're going to do better. You're going to get better at this stuff. Okay? All right. So what we're going to be looking at today, we're going to start with what is called orbital notation. And this is why you need your periodic table out, because we're going to be using the periodic table to kind of figure this out. Okay? Now, I want to talk a little about the way the periodic table is arranged here. Okay? Because this is going to help you a bit if we do that first. So let's draw out a kind of an outline of the periodic table. All right, so this is a general outline of the periodic table, okay? And the reason I drew this out is because it's helpful to know how the elements that are arranged on this periodic table fit into the pattern we're going to do with orbital notation, okay? So what we're going to do is tell you where these regions are on the periodic table. But these regions don't represent electrons. They represent the addition of electrons, okay, or adding electrons to the suborbital structure of an atom. That's not where electrons are, but it helps you to keep organized in terms of where electrons or when electrons are being added to certain sublevels and certain orbitals, okay? And so I want to kind of divide this up just a little bit. I wanted to put a line that goes vertically right here, and a line that goes vertically right here. Okay? And then I'm going to label this section right here as an S orbital region. An S orbital region. Okay? So we talked about S orbitals, okay? We did that yesterday. We said that in this drawing here, we have 2 S orbitals. We're showing an S orbital down here. That's the first primary level down that corresponds to this drawing we did for this sort of represents the way that you looked at it in physical science. And we have an S orbital up here, which is part of this second primary energy level. Okay? And all these p orbitals are also part of this second primary level. Okay? And so s orbitals are spherical. Okay? And then if we're adding electrons to p orbitals, we have to be over in this section over here. Putting a dotted line right there. So this is a p orbital region. Now remember, this is not where electrons are living or staying. Electrons aren't staying here on the periodic table. This is representing how you figure out where electrons are staying within atomic structure. So it's a p orbital region. And this section here in the middle, this is a d orbital region. And down here in the bottom is an f orbital region. Okay? Now the periodic table is one of the most important tools that chemists have for figuring out things about atoms and how one atom relates to another and their behaviors. Okay? But it's not perfect. Nature doesn't necessarily follow the same rules that we would like them to follow. Okay? So when we're talking about the way the periodic table is arranged, when we're talking about certain behaviors and certain properties, some elements don't really belong where they are. Okay? We talk about other properties, and then other elements don't belong where they are. All right? In this case, helium, which is located right here, so find your periodic table and make sure you can see that's where helium's located. It doesn't really belong there. When we're talking about sublevel regions of the periodic table, helium actually best belongs over here. Okay? Because helium is not part of the p orbital region, it's part of the s orbital region. Does that make sense? Now there are reasons why helium's over here. Okay, not the least of which is helium's a noble gas, and all of the other elements in this column are also noble gases. So it wouldn't make sense to make a periodic table with helium over here, because that's one of the main properties of helium, and it belongs over here. But you've got to know that sometimes things don't always fit exactly the way we'd like them to. We have to take nature for what it is. We can't make it obey our rules. Okay? So helium actually belongs over there, and as we do the orbital notation, hopefully the reason for that makes some sense to you. Okay? Everybody got that? All right, so let's go and actually write some orbital notations. Okay? So I'm going to put my periodic table right here just to help me keep up with what we're doing. And I'm going to start with the orbital notation for hydrogen because, hey, it's the first element. Okay? We said yesterday that this number at the top of this cell tells you the atomic number for hydrogen. It also tells you then how many protons hydrogen has. And as long as it's an atom and not something else, then it has also the same number of electrons. Okay? Hydrogen ions do not have one electron. Okay? But hydrogen atoms do have one electron. The one there tells you the protons. It does not always tell you the number of electrons. It only tells you the number of electrons if it's an atom and not something else. Okay? So, we have one electron in a hydrogen atom. And everything we're going to be doing today assumes all these atoms are in their ground state, which means their most stable state. Okay? And we're not going to have any ions, so we're going to be looking at these as if these numbers at the top actually represent electrons as well as protons today, okay, in this unit, but not for other things. But we're going to look at how those electrons arrange themselves. All right, so the first electron then, if it's in its most stable state, will be as close to the nucleus as we can possibly get it. All right? It's most stable when it's as close to the nucleus as we can get it. So we're going to have it down here in this first primary energy level, and see, that's an s orbital right there, isn't it? See that? An s orbital down here, this pink inner circle. Okay? So our first electron is in the first primary energy level and in an s sublevel. Okay? Since we can have up to 2 electrons in the same orbital using opposite spins, then we're going to show electrons by spin in this box, which sort of stands for or represents orbitals. Remember, orbitals aren't square. Orbitals are round or double balloon shapes and a bunch of other strange shapes we won't get into in this class. Okay? But this is kind of an address. All right? So we have 1 electron, and we always represent the first electron in an orbital with an up spin. Nothing special about up, but you've got to have one having one spin and one having another, but it's always thought of as having an up spin. Okay? And it has to do with things that kind of go beyond the scope of the class. But just for us, just remember, first electron in an orbital has to be up spin. Got it? All right, now, to get helium, which is the next element. So here's hydrogen. The next element on the row, number 2, here is helium. Remember, it really belongs over here in the S sublevel region. Okay? So for helium, then, we're going to write the element symbol and a colon, and that's required, guys. If I ask you to write on a test or a quiz or homework orbital notation for something and you don't write the element symbol, you lose points. Show me the element symbol. Okay? I'm from Missouri. Show me. Okay? Give me a colon. Always write a colon. Okay? All right. Helium is also in this first primary energy level, represented by your 9th grade version of electron structure here in this region. But in high school chemistry now, we're looking at this region. Well, guess what? There's only an S sublevel in the first primary level. Okay? So both the electrons in helium, and it's going to have 2, are going to be in that first primary level and that S sublevel, because I can get up to 2 electrons in an orbital, and in this case, the S sublevels only have 1 orbital, so I can get 2 electrons in the S sublevel. And so here's our box to show where the electrons belong in an orbital, and I've got an up spin. Well, the next electron has to have an opposite spin, right? So if that one's up, this one must be down. Now, I'm using a kind of a half arrow. These are actually supposed to be arrows. It's just faster to do a half arrow. Okay, if you want to do a full arrow, do a full arrow. Okay? Some people call it a fish hook. All right? But if you've ever gone frog gigging, you know they have a half arrow on the end. So that's an arrow. Huh? Okay, it's not a 1. It's an arrow. Okay, up, spin, arrow. Okay? All right. After helium, what's the next element? Lithium. Well, you know what's neat about the periodic table? It's arranged to help you figure out this stuff. And all the elements in this first row have electrons that are in their ground state, at least, being put in the first primary energy level. When you get to the second row, well, now electrons are being put into the second primary energy level. Okay? So here's the symbol for lithium. And we've got to have the same 2 electrons, or similar in structure anyway, the same 2, as we have for hydrogen and helium, because those electrons are still there in that first primary level. We've got to add 1 more electron for lithium. Lithium has 3 protons, and so for ground state atoms, not ions, but atoms, they're going to have 3 electrons. So I need another box for another electron, because I can only get 2 electrons in each orbital, the box representing orbitals. Okay? But now an electron's got to go into the second row, second primary level. Okay? So here's the second primary level. All right? Now, notice where lithium is located here on this region drawing I did. It's in the S orbital region. Okay? So we're also putting electrons in the S orbital. When you get to a new level, a new primary energy level, electrons always go to the S sublevel first. Okay? 2s. Okay? And so how many more electrons do I need? Just 1 more, and it's always got, the first electron always has to have what kind of spin? Well, the first one's always up. But you're right, opposite spins. And so that's lithium. Okay, now knowing what you know, see if you and a neighbor, if you want to talk to a neighbor and confer, see if you and a neighbor can figure out how to write the orbital notation for beryllium. Okay, so for those of you in the class here, I noticed that some of you are actually working together like I suggested. This is going to serve you very well. People learn well from each other. They solve problems well with each other. Okay, we are tribal or pack animals. Okay, so if you've been working with somebody to solve this problem, y'all pat each other on the back. That's good. You did good. Okay, if you work by yourself, if you're actually working to solve this problem, but you want to do it by yourself, yeah, you can pat yourself on the back too. But if you're waiting on me to give you the answer, okay, just go ahead and slap yourself across the face because you're hurting yourself, all right? You do well by trying to figure it out ahead of time. It helps you to solve problems by struggling to do this. All right. Even if you get it wrong, trying and failing is not a bad thing. The good thing about failing is that when you figure out how to do it right, you've learned more than if you got it right the first time. Okay? So failing is not a bad thing if you learn from it. All right? I want you to try to get past the idea that failing is always bad. Failing is not always bad. Okay? All right. So here is the electrons in 1s. Okay? Here we are in 2s. And there's the electron for lithium, and now there's the electron for beryllium. Not so bad, huh? Okay? So 2 tells you we are in the second primary energy level here on the periodic table, and it also tells you that you're in this second primary energy level here, and all of this stuff in this second primary level here. Okay? All right. All right, so let's take a look at the next element then. There's the next element. What region is it in? P orbital region. Okay, well, let's see how we can figure out how to do that. This is the symbol for boron. Remember, you always have to have the element symbol. You always have to have a colon. Okay? Boron. Okay? Let's see. All these electrons we had for beryllium are still there. At least in the way we think about it, they're still there. They're new electrons for boron, but they're still electrons in 1s and 2s because boron is building on what's below it. Okay? So we have the electrons from hydrogen and helium and lithium and beryllium in 1s and 2s, and then we're going to go to the second primary level and the p sublevel. So that'd be 2p. Okay? So here is the 1s set of electrons here. Here's the 2s set of electrons here. And now we're in the second primary level. We're in the second row of the periodic table. That's the second primary level. We're still in this second primary energy level here because we can put 6 more electrons in there. This second primary level here. So this is 2, but we're in 2p. Okay? So we're in this p sublevel region here, and we only need 1 electron. Okay, well, here's something you got to remember. You got to think about, okay? Once I start putting electrons in the p sublevel, all those orbitals are there, even if they have no electrons in them, because that's the way that electrons behave, okay? Remember, a single electron can join up with another electron. It can be in the same region because of opposite spins, but once you have an electron that you add another electron, it's got to be in some other orbital. It's got to be in a separate region, and so they arrange themselves in these regions we call orbitals, okay? And so even though there may be only 1 electron in these double balloon shapes like we did yesterday, all 3 orbitals are there, okay? So when you get to 2p, you must draw not 1, not 2, but 3 boxes. Okay? Now, we only need 1 more electron, right? And it has an up spin. So we're going to just draw it in this first box with an up spin. Got it? No, not really. You have to have 3 boxes because the orbitals are there, even though there's no electrons in them. Once you start putting electrons in the p sublevel, those orbitals form, even if the electrons aren't there. All right. Now we're at a point where I need to tell you about something I like to call the school bus rule. Okay? The school bus rule. So here's the way the school bus rule works, okay? Let's say it's the very first day of the very first day you're going to school, and Morgan is the first person on the route, okay? Going to kindergarten, the first day she's got to ride the school bus, okay? All right? Now listen carefully. So poor little Morgan, all lonely and scared, gets on the school bus. Where's she going to sit? Well, she's going to sit on a bus seat by herself, right? Kind of like this electron sitting here by itself. Got it? All right? Now, suppose Ty is the second person on the bus route. Tyrese. Okay? He's mean. Well, let's just say he kind of looks mean, okay? Maybe he isn't mean. All right. I don't know whether he's mean or not. Anyway, as a kindergartner, you think he's going to look mean? All right. Anyway, here's the deal. So the bus pulls up to his house, and he gets on the bus. He doesn't know Morgan, okay? He doesn't know if Morgan's mean or not, okay? Where do you think he's going to sit? By himself and not next to Morgan, right? All right. So when we get to the next element here, carbon, okay? Not only the school bus up there. It was the school bus rule. Remember, we have to have all three orbitals, even if there aren't electrons in there. So, just like Tyrese, here's Morgan sitting in the bus seat by herself, okay? And Tyrese is going to sit in the bus seat by himself. Okay? So boron just had one electron here in one box by itself. Carbon now has an electron by itself. Okay, now there's a couple of formal names for the way this works. Okay, the Pauli exclusion principle. I'm trying to think what the other name of it is. It'll pop to my head here in a minute. But the reasons why this happens, if you just think of the school bus rule, you can figure out how to do it. We'll talk about the formal names for these rules later. Okay? But this is the way it works. Okay? So if this is the way it works, that electrons, when they can, will sit by themselves. All right? Then let's see if you and a partner can figure out the orbital notation for nitrogen. Boxes represent orbitals. Once I get into the p sublevel, there are three orbitals. I have to show three boxes, even if some of them are empty. Three orbitals look like the models you made yesterday. No. There are more boxes later. Just it goes up by 2 boxes each time. Just bear with me. We'll get there. All right. Now look, guys. Here's the pattern. Nitrogen is going to have everything carbon had, and one more. So that's everything carbon has. Okay, school bus rule again. And this time, let's say it's Ashley. Ashley's the third person on the bus route. And she doesn't know Morgan, and she doesn't know Tyrese. Okay? And to her, poor little Ashley, she's, kindergartner, and she's scared her first day, and, she doesn't know what to think about Morgan and Tyrese, all right? So what's she going to do? She going to sit on a bus with Morgan or Tyrese? She's going to sit on a separate seat, just like this next electron. Okay? All right, let's get to oxygen now. Now, It just turns out that this bus only has 3 seats. Tiny bus. Okay? All right, one of midget buses, that's right. Okay? Well, this one only holds 6 students. Okay? So, only got 3 seats. Now, let's see. Who's going to be my next person on the bus? All right, Tyler's the next person on the bus. I'm sorry. Sammy, you'll be next, okay? All right. So, listen. All right, now, so there's a person on each seat. Tyler's got to sit with somebody, right? No. Actually, you got to remember this. Tyler doesn't really get to choose. He has to sit in the first seat. So whether he likes it or not, he's got to sit with Morgan. So there's Tyler. Okay? Okay. Now, we're already at oxygen, and I bet if you try and you confer with a neighbor, you can figure out how to do fluorine and neon. And so that's your next assignment in class, is to write the orbital notations for fluorine and neon, okay? Okay, let's see what we got. Fluorine's going to take everything that oxygen has here, and I hope the Thomas School Bus Company doesn't mind me using their picture of their school bus. I hope not. You know, I mean, this is like promotion. I'm not like taking any of their private information. This is public information. I hope they're okay with it. Anyway, so fluorine's going to have everything oxygen has. So all these electrons that oxygen has are going to stay there. Okay? But then fluorine needs one more electron than oxygen has. So we're going to put one more electron right there. There's Sammy. Yes, Sammy's the next person on the route. Okay? Yes. Just keep following along, okay? Are you working with somebody? All right. Now, neon's going to have everything fluorine has. Okay? But neon's going to have one more electron than the fluorine has, right? So one more electron. Let's see. Let's say that's Tyreek, okay? All right. Now, so now the school bus is full, okay, and it's got to take all the students to school before it can pick up any more students. All right? Notice it is full. Every time you fill up a row, you're filling up all the orbitals in a sublevel, or in a primary level, actually. When you get to the end of the row, you should have every orbital in every box full. Every electron, you have 2 electrons in every orbital box. Okay? You have a question, Sammy? Well, we're going to go to that. Hold on. Okay. Now, eventually, if we got down to here, that'd be what? Let's see. Yes, 59 boxes. We could. Now, we're not going to do that many. We're going to stop before we get to the F sublevel region. We're going to keep doing everything else until then. Okay? But you could do that. When you go to college, yeah, they may expect you to do 59 boxes. Okay? All right. So the next element we come to then is sodium. Now remember, some of these element symbols don't have symbols that look like the name because not everybody's American, okay? There are people who are Italian and German who name elements, okay? Or French or whatever. Sodium has to have all the orbitals and all the electrons in the same arrangement as neon in this ground state, the most stable state. So we're going to draw out all these boxes. Now let's notice where sodium is located on the periodic table, guys. It's on the third row. We can't put it in these 2-level orbitals. We have to put it in a 3rd-level orbital. And this is the S sublevel region. So sodium then, if we're using this illustration here like you did in 9th grade, it's going to have 1 electron up here in this 3rd primary energy level. Okay? And if we're using our high school version here, then we've got to have another primary energy level for sodium. Okay? And so this first energy level you always come to is S. Okay? All right. So now for sodium then we need a 3s orbital. And how many electrons do we need? More than what neon had? Just 1 more. There it is. Okay? All right, then let's everybody do magnesium. Now, while we're on magnesium, let me be careful because students get this confused. This is magnesium. Okay? This is manganese. 2 different things. They sound similar, but magnesium symbol is Mg and manganese symbol is Mn. Please try to commit the memory that you're not going to confuse those, okay? Mg is magnesium, Mn is manganese, okay? All right. I want you to do the orbital notation then for magnesium. Here is the blank boxes for magnesium. Okay, it's going to have all the electrons that sodium had. Oh, that should be a down arrow. Notice I'm putting 1 electron in each box up and coming back and pair them up. Okay, that's the way they fill up. That's the way I'd like you to remember to do that. Okay, and since I've got a kind of a double arrow thing here, I'm going to erase this little top thing here to make sure we're making that clear. It's a down arrow there. So magnesium has the 1 sodium in 3s, 1 electron that sodium has in 3s, but it's got to have 1 more, so that's magnesium. All right? All right, now somebody was asking me specifically about aluminum a minute ago, but I bet now that she and everybody else can do aluminum. What do you think? Let's do aluminum then, okay? Everybody do aluminum.
Would you just add a box of 3s?
Well, now you got to go to 3P. 3P.
Why would we be going to 3P?
Because you know the 3rd row is 2.
So why would it not go to 3S?
Because it's
Okay, so aluminum is going to have all the electrons that manganese has. But aluminum is right here on the periodic table. So now it has electrons that are in the p sublevel region. Okay? And so this last electron in aluminum has to be in a p sublevel. Okay? And this is in 3p because we're in the 3rd row. 3rd row, that's 3p. Okay? There are always 3 orbitals in 3p, even though there may not be electrons in every box. Okay? But we only need 1 more electron. And just like Morgan earlier, it's going to that first school bus seat or the first box.
I did it right.
Yes. All right. We've reached a point now where we can skip a few, I think. And I'm going to give you the first of your homework problems tonight. Okay? Just the first one. There'll be more. Okay? Well, just find your periodic table and find the element number and just do it. This is your homework. Now I'm going to move on. Okay? Just saying. We're moving on. Now, I'm going to go and skip over to sulfur now, okay? Just to make sure everybody's kind of on the same train, hopefully.
So this is homework or we just gonna?
No, homework is for phosphorus. We're going to skip over phosphorus and go to sulfur now, okay? So sulfur is still in that P sublevel region in this third row, so it's in the third primary energy level or represented in the third primary energy level on the periodic table. It's going to have all the electrons that aluminum had. Sulfur. One S, 2S, 2P, 3S, and 3P. All these orbitals down here in the lower levels, they're going to be completely filled up. Okay, 3S is filled up. There's the electron for aluminum. Sulfur, though, is going to have 1, 2, 3, 4 electrons in that P sublevel in the third primary level. Okay? So we're going to have 4 electrons in 3P. Does everybody understand what I'm saying? All right. It's right here, number 1, 2, 3, 4 in the P sublevel region. So I need 4 electrons in the P sublevel. 1, 2, 3, and then pair up for 4. There's sulfur. Got it? All right, I'm going to get rid of the school bus here. Got it? It's always up arrow first. It's kind of beyond the scope of the class to explain why. So just take my word for it. It's got to be an up arrow first, okay? Up, down, okay? All right. Let's have you guys practice with argon. I want you to practice with argon. All right? Work with a neighbor if you want to and do argon, okay? You're doing argon as a class assignment. Okay, so argon then is all the way over here on the far right. It's a noble gas. Okay? And so we just finished up with sulfur here, so I just need 2 more electrons to get to argon. So argon's going to have all the electrons in the same structure as sulfur. So all the electrons that I have for sulfur, 1 up arrow in each box, come back and pair them up. And so here is what sulfur looked like. I need 2 more electrons, so I need 2 down arrows in those orbitals there, and that's argon. 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 Okay. Sulfur had 16 arrows and argon has 18. What?
Put 3 boxes in 3 feet.
Yeah.
Instead of putting 1 arrow in 1 box and then another arrow, why you don't put them?
Because Morgan, no, that wouldn't be Morgan. That was, who was that? That was Tyrese and Tyler didn't want to sit next to anybody because they didn't know anybody.
Well, no,
All right.
I decide Morgan.
Well, whatever. I'm just saying, you get the picture, okay? All right. Okay, let's go to the next row. How about we just skip over potassium and go straight to calcium? What do you say? See if you can work ahead. I'm going to go ahead and do it on paper. You can go ahead and do it for yourself and see if you can get there before me. See how good you're getting at this. Okay, how did you do, guys?
gonna have to put 4 feet.
Not yet, not for calcium. Right, next I need to have some p orbital stuff, but first we got calcium there, and that only has 2 electrons and 4s. And so that's calcium. Okay? Got it? All right. Not got it yet? So, now, in some textbooks and some people, they do it, their orbital notation might look a little bit different. They'll do circles instead of squares, or they just do lines and do the arrows on top of them. You know, but it's all kind of the same thing. Once you learn to do it, then you know how to do it. You can recognize it, okay? Excuse me. Now, everybody kind of getting this at this point? Good. All right. Well, good. Good for you. Now, look. Up to this point, we had practice. Okay. I know it's kind of this has been fun and everything, but I'm going to kind of twist it up a little bit for you here. Now, I'm sorry. I'm not twisting it up. Nature twisted up. Okay. If you want to blame somebody, you can blame God for this, but I wouldn't do that if I were you. Just saying. Okay. All right. Because something funky happens when we get here. Okay? This is the D sublevel region. Okay? All right, now listen to me. Without trying to get into all of the arguments and understandings of why it does this, okay? Because it really kind of goes beyond the scope of the class. I don't want to bog us down too much. Here's what happens when you get to a D sublevel. You've got to drop back 1 primary level. It's as if these electrons right here don't belong here. They belong right here. Huh? No, you would have 10 boxes here. I mean 5 boxes here for 10 electrons. Okay? But they're going to be like in the third primary level instead of the 4th. Let me show you. You don't move it up 1, you just back the number up 1. Let me show you. All right. Here we go with scandium.
Which one is it?
Scandium. Scandium. All right, so scandium is going to have all the same electrons that calcium had. Okay? In fact, I'll just put it right up here above it so you can kind of see what I'm doing. Okay? All the same electrons as calcium. Everything stays the same, but we're going to add to it. But the way we add to it is a little bit funky here. Well, it's not that bad. It's just a little bit different. That's all. We'll be okay. You'll get it. All right. So all the same electrons are there. 1 in each box. Come back and pair them up. 1 in each box. Come back and pair them up. And so there's all the electrons for scandium. So let's start by putting the right number of boxes for this section here. Now remember, this is the D sublevel region here. Okay, D orbital region. How many atoms do we have from scandium to zinc? 10 of them. So how many boxes do I need when I get to a D sublevel region? 5 boxes. Very good. You guys are getting that part. That's great. So when I do this D sublevel region, I'm going to need 5 boxes. 1, 2, 3, 4, and 5. Here's the only tricky part. This is a D sublevel region, but the tricky part is when I get to scandium, it's as if we're really putting electrons here in the 3rd primary level and not the 4th. That's kind of a gap right there. You see the gap? Okay, so this is going to be 3D and not 4D. All right? And so for everything else is the same. Just put, instead of 4D, it's 3D, and we use 1 up arrow there for scandium. So everything in this D sublevel region drops back 1 primary level. This right here, this is 3D, that's 4D right there, and 5D. Okay, got that? Why do we do that? Because that's the way it actually behaves. It's actually more complex than that. But we're kind of simplifying it a bit. All right. Okay. Now, So, but that's a good question, so let me address that, guys. In high school chemistry, we do super simplify things some, okay? That is to say, the behavior of electrons in the D sublevel are a bit different than what we're actually using, but we're trying to do it this way because it's simpler for right now. When you get to college or in a higher level chemistry class, you may be expected to know how D behaves a little bit differently than it seems to make it behave. Okay? But for right now, it's a good place to start with it. Got it? It's just like when you were in ninth grade and you learned your primary energy levels, and now we're going to sublevels and orbitals. Okay? We're adding to what you knew before, but it kind of changes what you knew before a little bit. All the electrons represented by the position of these atoms here are 3Ds.
What about the second round?
This is 4Ds.
So you still go across and count it. You don't go down the road.
No, you don't go down the row and count it. It's still across. Okay, so there's scandium. Now, let's do vanadium. What do you say? Vanadium. So eventually, we're going to get to long things where you want to turn your paper sideways. Okay, so here we are with vanadium. Vanadium is right here. Okay, and I've got 1, 2, 3 electrons represented by the position of vanadium in the periodic table. 3 electrons in the 3D sublevel. And using the school bus rule again, we do 1, 2, 3, and we're done with vanadium. Okay? You got that? Do we need to practice another one in this region? I'm going to give you one for homework, but I'm asking, do we want to practice one more in here? Everybody's good with that? So it follows the same pattern. This is 3D. We started in 4S and went to 3D. Here we'll be in 5S going to 4D. Here we're 6S and going down to 5D. Okay? Now, here's the tricky part, if it's tricky at all, is that this over here, we started in 4S. This is still 4P. Okay? Got that? All right. You want to do one practice in this row? As homework or practice? Homework. All right, here's your second homework problem. And then as class practice, how about we do arsenic? Arsenic. Okay? All right, we got all the lower level orbitals and orbital, primary levels, sublevels, orbitals, and electrons. One electron, pair them up. Oop. I don't know what I'm doing there.
What about for the ones in the S orbital region instead? How does it count there?
This is the class practice problem, arsenic. I'm hoping you guys are working ahead of me. And so now, when we get over here to arsenic, this is the fourth row, so we're back into 4P over here. Okay? 3D, then back up to 4, I'm sorry, not 4D, but 4P. Sorry about that. And you got 3 orbitals in 4P. Arsenic is right here. 1, 2, or 3 electrons in 4P. 1, 2, 3. Okay? Because arsenic is right here. It's in the P sublevel region. Okay? It's in the 4th row, so this is the 4P region here. Before we leave, we've got just enough time, I think, to do one more, make it kind of a tough one. How about we have everybody work on, how about indium? Indium. Okay, so here's the actual solution to this problem. It's kind of long. Notice I've turned my paper the long way, or call it what you want, I guess. But anyway, we filled up 1s, and then 2s and 2p, 3s and 3p, filled up 4s, dropped down one level to 3d, filled up 3d, and that has 5 orbitals, and now we've gone back up to 4p, and then we get to 5s. So indium is going to be in the 5th primary energy level. Indium is right here. If you go back over to the left and count the number of rows, 1, 2, 3, 4, 5. So it's in the 5th primary energy level. So we're in 5s. So here is, indium's right here. Here's 5s. Then we drop back one level, 4d, and fill all that up. All right, 10 elements, 5 boxes to get 2 electrons in each box for 10 electrons for each of those 10 elements. And then finally, indium is right here, the first one when we get into the 5p sublevel region. So we have only 1 electron in 5p.